here, and you can find what is the current. Okay. Now, problem number 5. Now, in this problem, as you can see, we have aluminum wire, diameter is given, the current is given, we have to find drift velocity, and the density of the aluminum is given. Now, as you can see here, it has gram divided centimeter cube, so all has to be converted into SI unit. The same thing with the molar mass, which is gram mole, so gram has to be in kilogram. Avogadro's number is given. So how can we solve it? Now, so let's write down the given values. The D is given, which is 1.628 millimeters. So it has to be in meter, okay? The current is given, amperes. We have to find drift velocity. So the formula of the drift velocity is what? Drift velocity is equal current divided by number of charged particles or charge density. Sometimes it's written E or Q, okay? N times E or Q multiplied to the area, okay? Now the area, we know that it's pi r squared over 2 of the wire, or since it's D is given, that means area will be pi, sorry, this is a pi r square, right? The area. If it's a diameter, that means D over 2 squared. So that will give you pi D squared over 4, correct? Okay. If that's the case, then now, so the N is a charge density, okay? So it itself is equal number of particles or charges divided by the volume, okay? Now E or Q, we know it, which is equal 1.6 times 10 to the power of minus 19, okay? Now, we know that N is equal mass divided by molar mass, or number of particles divided by Avogadro's number, correct? So we have to somehow get it into here, okay? We also know that the density is equal mass over volume, correct? So that means we can get from here the volume. Volume is equal mass over density, correct? And number of particles, which is this one, we can get it as number of particles is equal m times Avogadro's number divided by molar mass, correct? So the charge density, which is small n, is equal, n will be equal to m Na divided by molar mass. And the volume will be m rho, correct? So this will cancel out. So we end up with rho Avogadro's number divided molar mass, okay? So finally, we can bring it everything here. So V drift velocity is equal current, N will be rho Na divided molar mass multiplied to the charge, E or Q multiplied area will be pi D squared over 4. Okay. Now you have to plug the numbers and get the value. Okay. The next question will be 8. So I try to first focus on the medium or difficult problems. And if we will have time, we will solve easier problems or easy problems. Problem number 8. In the problem number 8, let's write down the given values. So the diameter is given of the wire, which is 2.54 centimeters. The length is given 20 centimeters. Resistivity is given, and the potential difference is given, which is 3 times 10 to the power of 3. Okay, we have to find the current. So the current is equal delta V over R, correct? Delta V is given, so the resistance is equal resistivity times L divided by area. Now, since the diameter is given, we know that rho L, this will be pi d squared over 4, correct? The area of the wire, of the cross section. So that's it then. You just have to put everything there, delta V over rho L. Okay, sorry guys. So this will be the, okay, delta VR. Okay, so that means it will be rho L divided pi d squared over 4. Okay. Okay, what else? Okay. Now, question number 9. Okay, so in this problem, we have given initial temperature, right? 28 degrees Celsius. We have to find final temperature when R final is twice of the R initial. So in general formula for such a problem is final resistance is equal initial resistance 1 plus alpha delta T. Delta T is the change in temperature. So we know that we have to find T final when R final is equal to R initial. So that means R final, we can write down as 2R initial is equal R initial 1 plus alpha delta T. Now the alpha is given. So R initial will cancel out. That means 2 minus 1 is equal alpha delta T. So it gives you 1 is equal alpha delta T. So 1 divided by alpha is delta T. Then 1 divided alpha, delta T is equal T final minus T initial, right? So T initial goes there. All right, plus T initial is equal T final. That's it. T initial is 28 degrees Celsius. Alpha is given. Any question? Okay. Have you covered chapter 10? Just a moment, guys. Okay. This is chapter 9. This is chapter 10. Here we have problem number 1. Problem number 1. Okay, let's look at the problem number 2. Problem number is just to find equivalent resistance. It's easy, so you can solve it yourself. Problem number 2. So in this problem, all of them are connected in parallel, right, to the plug. That means if that's the case, so VA, here we have so let's assume it as a resistance, all these things, okay? So we have power consumption of the toaster, 100, this one, watts, then power consumption of the speaker, which is 95, and then power consumption of the lamp, which is 71, all connected in parallel, okay? If the current is passing here. Now, when 3 devices are connected in parallel, the potential difference across all of them will be the same, okay? So delta VAB is equal, like toaster, speaker, and lamp, okay, when they're connected in parallel. But the current will be different. So this current, let's say there's a certain current which is coming from point A. When it comes to this point, it will divide into 3. They will not divide equally, but depending which one is consuming what current. So we have to find how much current is consumed across the speaker S. So the formula will be what? In general, power is equal current times delta V, right? That means if you want to find PS is equal current of the S delta V. That means IS is equal PS divided delta V. Now, when it's connected in parallel, potential difference across all of them will be the same. So therefore, 1495 divided delta V was equal to what? 120 volts, okay? So that will give you 12.45 amperes, okay? Any question? Same thing you can do for the toaster or lamp. Obviously, lamp will consume less current, or less current will pass through the lamp because it has less power consumption. So IL will be PL divided delta V. So 75 divided 120. Okay, Now, more interesting is coming. Problem number 3. Have you covered Kirchhoff? Okay, so anyway, I will explain. It's not difficult. There's a few things that you have to know, and you can apply the same principle or technique to solve any problems. Is it possible to draw it here? It's impossible. Okay, I think we can draw it in this way. Now, first of all, we know that when you have such a circuit, you have to solve such a problem using the Kirchhoff's law. Kirchhoff's law says that sum of voltages in a loop is equal to 0, and sum of the current in a junction is equal to 0. Okay, so we have to find what is the potential difference across V2, correct? If that's the case, we have to first draw a loop. So I always try to draw a loop starts from negative to the positive of the potential difference. That means in this case, I will draw a counterclockwise loop, okay? Because now, as you can see here, it starts from minus to plus, okay? And therefore, it will be counterclockwise. If that's the case, then now we have to write down some of the potential differences are equal to 0, correct? So when you have this loop, you have to look at the potential difference. So starting from minus to the plus, okay? So if you go here from minus to plus, that means you have to write down positive. So positive V2, okay? Always. If you draw the loop opposite, clockwise, that means starts from plus, ends in minus, therefore it has to be negative V, okay? But in this case, we draw it loop. It's up to you how you're going to draw the loop, okay? In my case, I made it from minus to the positive terminal of the battery. Therefore, I write down positive V2. Then you have to follow the loop, and it comes across R2. When current passing along this loop in R2, there will be potential drop. That means potential drop means minus 4 ohm multiplied to the current, which is 3 amperes. Okay, I will not write units, okay? 4 ohm multiplied 3 amperes. It has to be negative because it's going along. So if I draw it loop like this, in the direction of along the loop, be negative, okay? However, if the current is going opposite, then it has to be plus, okay? Plus IR and negative IR, okay? Or in other words, minus V or is equal plus V, okay? Because we're going to sum all the potential differences and make it equal to 0, okay? So minus 4 ohm multiplied 3 amperes, and then we come to the resistance 4. So what should I write here? What current is passing through R4? Current 6. No, look at the down. So current 6 goes and passes here. So this is current 6, correct? So that means it's opposite, correct? To the direction loop. Therefore, I have to make it plus R4 is given or not? Is not given, correct? We don't know. So therefore, 1 amperes multiplied to the R4. We don't know still R4, okay? That's what we may find it. Okay, so that's equal to 0. Okay, let me write it down with a bigger things. Minus 12 plus R4 is equal to 0. Okay, so now we got our first equation, which is sum of the potential difference are equal to 0. Now, we cannot still find V2 because we have the two unknowns, which V2 and the R4, correct? Now, we have to come up with another equation, okay? Now, what I'm going to do is that I'm going to select the right side of this loop. I'm going to draw again another loop. This one, like this, okay? This will be the second loop. This is first loop, so this is first loop. Now I'm going to draw a second loop. This time you have to tell me. So I start with V2. What should be the sign of V2? Positive, correct, because the loop is going from minus to plus, correct? The V2. So positive V2. Now it's going along the R3. What should I write down for the R3? Correct. Current is going opposite to the loop, which means it's adding potential difference. It's like a charging, discharging your mobile phones, okay? So that means I have to write down positive 6 ohm to the 1 ampere, correct? Now, let's look at the R5. R5 minus 4 multiplied to the 3 amperes because I5 is passing through the R5, correct? I5 is passing through R5, correct? Then is equal to 0. Now let's write down properly. We got V2 plus 6. No, wait a minute. 6 minus how much? 2, correct? So that means V2 minus 12 is equal to 0. Actually, we could just jump immediately to the second equation, correct? Anyway, at least you know. So that means V2 becomes just 12 volts. Huh? Wait a minute, 6 minus 12, correct? It will give you minus 6. So if it goes to the other side of the equation, it will give you plus, correct? Plus 6 volts. Okay, so actually you could just look at the second loop immediately, right? Instead of writing everything. So V2 in this case is equal to 6 volts. Any question? Now, let's then move to the next problem. Next problem will be, so let's this one. Problem number 4. Now, as you can see, I think problem number 3 are for the same, right? the circuit itself. Now we have to find R4. We got the first loop that I just deleted. Actually, I shouldn't be deleting it. Anyway, so let me write it down. The first of all, we found that using this loop, second loop, we found that V2 was equal to the 6 volts, right? Now, in this case, for the loop 1, what we got? Can you tell me? It was V2, right? Minus 3 multiplied 4 gives you 12, right? And then plus R4, correct, is equal to 0, right? So since we got 6 volt for the V2, we can write down 6 minus 12 plus R4 is equal to 0. That means minus 6 plus R4 is equal to 0. So R4 becomes 6, correct? Is that clear now? Okay. Okay, let's move on then. Problem number 5. We have to find V1. This time I have to check your understanding, okay? Okay, let me start doing it and make a screenshot. So we have to find V1, correct? Okay, now how should I draw the loop? Clockwise or counterclockwise? Clockwise. Okay, so we know that sum of all voltages is equal to 0, correct? So let's start from the battery. What should I write down? Plus V1, then minus 6 multiplied 4 amperes, right? 6 ohm multiplied 4 amperes, then minus 6 ohm multiplied 1 ampere, and then minus 4 ohm multiplied 3 amperes. Okay, right. So 4 multiplied 3 amperes is equal to 0, correct? So that means V1 minus 24 minus 6 minus 12 is equal to 0. So the V1 will be equal to how much? 42 volts, okay? It's not that difficult, okay? Is that clear? Okay. If that's the case, then let's move on. Let's look at the problem number 6. We have to find current 2. Okay, let me delete this one. So in this problem, in the 6 and the 7, we have to find current 1 and current 2. Okay. Okay. Okay, let me draw the loop. So first, look at the left side. Okay. Look at the left side of the problem number 6. How should I draw the loop? Clockwise, correct? What about the right side? No, counterclockwise, because I try to always keep the battery as a positive sign. Okay. So I'm going to draw the right side is counterclockwise. It's up to you guys. Whether you make clockwise, counterclockwise, you will get the right answer, okay? Okay, so now let's write down equation for the number one, loop one, okay? So we start from battery, which is 24 volts, correct? Then it comes to the R1. What should I write down, R1? Minus 8 ohm multiplied current 1, correct? Then it comes to the R2. What should I write down for R2? Minus 6 multiplied I2 is equal to 0, okay? Kirchhoff's law, sum of the voltages in the loop is equal to 0. Now, let's write down for the second loop equation. What should I write? We start from battery, 10, then it comes to the R1. What should I write for the R1? Minus 8 current 1, and then R3. R3 is current is going opposite to the loop, right? So therefore it's a plus 4I3 is equal 0, correct? So as you can see here in this two equation, we have three unknowns, correct? We don't know current 1, current 2, current 3. That means we have to come up again with the third equation. Do you agree with me? Now we're going to use current junction. So we select this point, okay? We select that point. Can you see it, guys? We select this point, okay? Which means, say, all the current that is going into the junction is equal to 0. That's current Kirchhoff's rule, okay? So now we know that current 1, current 3 is entering into the junction, correct? To the point. That means current 1 plus current 3 should be equal to current 2, correct? So this is our third equation. Now, what is next now? So what we can do is this one. We can take current 2. Okay, we can take current 2, put it here, okay? And then we can take current 3, bring it here, okay? And then we can find, no, we can find first current 1, okay, I1. Once you got I1, then you can bring the I1 into here. You can find current 2 from equation 1, okay? And since you know current 1, current 2, if you know current 1, you can bring to the second equation to find current 3. Any question? Okay, so by doing so, we solve it question 6, question 7, okay? What else? Okay, now there is one more problem, I think, which is okay. Problem number, okay, chapter 1. Okay, let me delete this one. So let's go back to the problem number. Okay, problem number 11. Let me draw a circuit for the problem number 11. So the problem number 11, the capacitor and the resistor are connected in series. Okay, first capacitor is fully charged. Okay, first capacitor is fully charged, and then it's connected to the resistor to discharge the capacitor. Okay, we know that the capacitance is given as a 3.77 farad, and the potential difference across the capacitor is given as a 4.05 volts. Okay, so if you put here the potential difference V, you will find VC is equal 4.05 volts. And when the capacitor is discharged by the half, so let me write down as a Q final, when it's discharged, initial of the Q is half 2. So that means when the capacitor is fully charged, it had full charge Q initial. Okay, now when it's connected to the resistor, the capacitor had half of the initial charge. Okay, so we have to find how much energy was delivered to the resistor. In other words, how much energy was delivered, final energy to the resistance. So that means we have two states, right? In and final. Do you agree with me? So initially, when capacitor is fully charged, so how can we find initial energy of the capacitor? What is the formula? 1/2 CV squared. Okay, this is V is the potential difference across the capacitor. Okay, now if you plug the numbers, 1/2 C is what? 3.77 multiplied 4.05 squared. How much you will get? Initial energy of the capacitor when it's fully charged will be equal to the, if you calculate, it will be 30.918 joules. Okay, when a resistor just connected to the capacitor, or before connecting to the capacitor, initial energy of the resistance is equal to what? Yeah, 0. Correct? There is no charge still before connecting to the capacitor. Okay, so we have to use conservation of energy where energy initial is equal final. Okay, energy is not disappeared. So when we connected the resistor to the capacitor, total energy which stored in the capacitor will be delivered to the resistor. Correct? That's what we have to find. Now, what is the suggestion now? We have to do now. We have found initial energy of the capacitor. Can we find final capacitor? What is the initial charge was stored in the capacitor? How can we find it? Initial charge. What is the formula? Initial. We can find how much energy was stored in the capacitor initially. What is the formula? Capacitance multiplied to the V. Correct? V is the potential difference across the capacitor, okay? Which means 3.77 multiplied 4.05. How much you will get? 15.26 coulombs. Okay, this is the total charge was stored in the capacitor initially. Okay, now final charge in the capacitor was half of the initial charge. When half of the charge is stored in the capacitor, we have to find how energy was delivered to the resistor. Okay, so in other words, certain energy which was stored in the capacitor initially, when it connected to resistor, will flow or move, transfer to the resistor. Okay, so final energy was what? 15.26 divided by 2, it gives you 7.3 coulomb. What is next? Tell me. We found initial energy was stored in the capacitor. What we can find now? We know how much charge is there in the final. Okay, finally, so the energy final in the capacitor is equal Q squared over 2C. Okay, why I selected this formula, not V? Because C is constant. Capacity is constant, okay, in the capacitor. And we know the charge. So that means 7.63 squared divided by 2 times 3.77. So that will give you 7.729 joules. Okay, now we found final energy in the capacitor. So what will be the equal, how much energy delivered to the resistor now? What we have to do? Yes, initial minus final. So that means delta V, okay, delta U final of the resistor is equal to the U initial of the capacitance minus U final capacitor. That will give you how much it was delivered to the resistor. Okay. Okay, guys, that's it. Recording.